Hi, Robin here. Good look at compression. This is aimed predominantly at the OCR A-Level Computer Science, but we'll talk about things in here that are appropriate for other exam boards. So, for example, I'll talk about Huffman Encoding, which is in the AQA exam board as well. With compression, what we're ultimately trying to do is reduce the file size, and therefore we can reduce the amount of memory that's taken to store whatever it is we're working with. Therefore, we have different file types that exist, and also if you think about the actual quality of the thing that it is you're using. So, for example, if this was a picture, we can look at things like the resolution, so in other words how detailed that image is, and we can look at the size of it. So an image that would be big enough to go on the side of a building is obviously going to take up more memory space than one that's the size of a postage stamp. So again, we can kind of use that to our advantage, and obviously depends on the scenario we're in as to whether that's appropriate or not. With compression, we can use a ratio, and therefore we can make comparisons between different file types. You can see here the size of the compressed file divided by the size of the original gives us that ratio, and obviously the closer to zero the better. There are two main types of compression algorithms we need to be aware of. There's lossy and lossless. The first one, lossy, if you notice with this, we get a really small compressed file. And it's really useful for that. So if you're working in a scenario where you really need to compress it really small, perhaps it's being sent over the internet or something like that, then this can maybe be a better method to use. However, we have to do this with the awareness that it doesn't restore back to its original value, and that can be a problem, particularly if you wanted it to restore back. So say, for example, you're a photographer, you've taken really high resolution image that you want to be able to sell to customers. You don't want to then compress it and then reopen it again and find that you've lost really important detail or something like that. So it needs to be appropriate to the situation you're in. Whereas if you're doing something perhaps more for a website where you need it to be quick to travel over the internet, but you also need it to be able to then display clearly on the web page, this may be more appropriate, because again, the file size and the image appearing on the screen is going to be much smaller anyway, and therefore perhaps less of an issue. But again, we have to be very kind of circumstance to when this is appropriate and not. Again, you can see here on the right hand side, I've got an original copy of the logo, and then you can see the lower version has been a compressed version of it. You can see that the quality of that is much less, it's much more pixelated, it looks dirtier, doesn't it, as a result of that. And again, we wouldn't be able to return back to the original value with this method. In comparison, we have lossless compression. Lossless compression, you'll notice, returns back to its original size, but the compression size itself is less as a result of that, because we're having to retain more information to be able to return it back to its original value. So again, we need to do this when it's appropriate to. So like I said before, scenario where you wanted to protect the original quality, but you just wanted to, say, transport or store that data temporarily, this is a much better way for you to do that, such as the photographer example I gave earlier on. Again, like I say, it's very circumstantial as to what's appropriate. So, as I said, we're aiming to get rid of redundant data, and we're looking for patterns in the data to do this. And then, like I said, the big benefit of this is that we're trying to maintain the original state of the file. We're not losing anything. A classic example of using exam questions for this would be text-based things, where if you're going to start dropping letters out of the words, it would mean that the whole document would no longer make sense, would it? The text wouldn't make sense anymore. So therefore, they would use this as a good example in that. We're going to look at two main methods of compression now: run length encoding and dictionary encoding. With run length encoding, what we're looking to do here is look for patterns. So you can see that in this particular example, I've got 8 R's next to each other. In other words, what we can do is represent that as just R8. It's worth mentioning that sometimes you'll see a flag character. The flag character will be something like a $sign, usually used, possibly a hashtag. And again, what they're doing there is to represent that a compression has taken place. The only thing with this is that though it does reduce it down, as you can see in the one below, so with the A's and then the B's and the C's right through to the D, E, F, that what it turns into is much shorter. However, you've got to think about, well, how often does this actually happen in the English language? How often do we see this in text? It's not very common, and therefore the actual benefit of this, it can be much less. Again, if you think about how many words in the English language even have duplicate letters, that would benefit from this. So it's very, again, circumstantial as to when this would benefit. A better perhaps use of this would be more something like images, where we can represent images, because you're much more likely to get multiple colours next to each other than you are to get multiple letters. So an example here, you can see we've got an image, dead simple image with a green area, blue area, and then two red areas. But because of that repetition, we're now getting an opportunity to reduce this down. So as you can see here on the right hand side, because there were 6 G's on the left, we can see we can write that instead as just G6. So instead of having to have 6 bits to store that, we can now store that in 2. And I do think you can see that this is much more obvious, and actually what this would reduce this down is it would halve its size to do this. We'd get a ratio of 0.5, and again we can therefore compare how successful that is to do that. Another alternative is dictionary encoding. A simple example here, we've got the Shakespeare to be or not to be, that is the question. And because in that sentence there's a repetition of words, so to be or not to be, because to be is said twice, we can therefore put that in the table. And rather than having to keep saving each letter of the character, instead we just call the position, its location in the dictionary. So you can see that we then end up with the sentence, the encoded part over here, where it says 1, 2, 3, 4, 1, 2, because the 2B has been repeated twice, and therefore we're saving. And obviously if you've got text or sentences where there's a lot of repetition, you're really going to get the benefit from this. I think the advantages of dictionary encoding are perhaps obvious in many ways. The fact that you're reducing repeated values will therefore reduce the data size, therefore reduces the memory consumption, therefore reduces the processing required, which obviously makes that faster, more usable, increases like transfer speeds across networks, reduces download speeds, upload speeds, etc. So really quite a useful method. The downside of dictionary encoding, however, is the cost of the dictionary itself. Obviously that's additional to the code that you're sending, and there can be situations where because of that cost it actually means that you don't really save much data at all, or if any, and therefore you have to make a decision as to whether this is the appropriate method or not. Another method of compression is Huffman encoding. Huffman encoding works on the principle of frequency. By considering which data types are being used more frequently than others, and therefore giving the most frequent ones the smaller bit lengths to store them, you therefore make a saving in turn. So as you can see from the graph, the letter E is used more frequently than the letter Z. The idea of that would be, therefore, that because we would need a minimum of 5 bits to store 26 different elements, if we give the letter Z the full 5 bits, whereas we give the letter E just a single bit to store it, we can therefore use the letter E 5 times before it's come at the same cost as the letter Z. And therefore, because it's more frequent to happen, it should give you then a saving in turn. I'll show you an example of this in a moment. There are many different methods for Huffman encoding, and in many ways the flexibility of this is what makes it so useful, because you can apply it to your different scenarios. As you'll see as I show you this, the Huffman encoding uses insertion and cues, and therefore there's a decision point as to where you insert the next piece of data. Would that be in front of older data? Will new data go after older data because of the nature of a queue? And really the priority therefore is the decision of whoever's writing that algorithm. Again, some people will prioritize building the encoding tree from the left, others from the right. I'm going to balance it as much as I possibly can to sort of give that convention. In many ways, balancing is the better method, because you should theoretically get a reduced data set, though to be honest you do tend to end up with similar data sizes regardless of the method you choose. Okay, so the first stage of Huffman encoding is to take our sentence and to look at the frequency of the letters within the sentence. The first letter therefore is capital D. It's worth noting that a lowercase d would be considered a different letter and therefore would need a different code to show it. We'll look at the D and there's only one of them, so therefore we have a frequency of 1. Our next letter is E, and there's actually 3 of them, so therefore a frequency of 3. This one is N, of which there's 1, 2, 3 of those. Then we have an I, of which there's 2 of them. And then we have an S, of which there's 2 of those as well. We then have a space, and there's 3 of those spaces. So I'm just going to put SP to represent that, and there's 3. Then we've got an A, of which there's 2 of them. We've then got a capital M, of which there's only 1. And we've done all of the letters except for the C, of which again there's only 1 of those. The first thing we need to do now is to order this, and what we're actually going to create from this is a queue. So what we can do is use like insertion sort to do that, and therefore by insertion sort we'll preserve the order of these letters. You could obviously use other sorting methods, and again, one of the things I sort of previously talked about how there can be different methods to use this. There's no rule that says that an E has to go before an N, but there can be different conventions. It could be that you go alphabetical, for example, and that become part of your influence. I'm just going to preserve it in the same order that it's currently written in, except for changing the frequency. So in other words, I will keep the E in front of the N and I'll keep the I in front of the S. Okay, so as you can see, I've done that, and you can see that we've now got a frequency order. This is a queue, so therefore we have a head and we have the tail just off at the end of the table, don't we? Once we've now done that, we then start to create a tree from it. The idea of this is we are looking to do pairs, and we're always pairing within the queue. So in other words, I'm going to pair D with M. So I bring in D and M. D has a frequency of 1, M has a frequency of 1, and therefore when they're joined together, they have a combined frequency of 2. What we then need to do is, because this is a queue, we need to reinsert them into a queue. Therefore, because these have a combined frequency of 2, I'm going to bring them and I'm going to put them here. And again, this is, like I said, there's different choices for this. Some people may choose to put the I in front of it and the S in front of it because they're older data. I'm just preserving the order that they're in, so hence that's my justification for putting it here. Okay. We then join up the next two, so we've got C and DM, so therefore I'm going to write C here. C has a cost of 1, and therefore when they're combined together, they now have a cost of 3. Again, combined, they're now going to go here within the queue. And then look to combine these two. Notice neither of these are in the current tree that I've created, so I'm actually going to draw them separately because I might want to move them around depending on how the tree sort of pans out once it starts to be built. And what we're looking to do is try and make the tree as balanced as we possibly can as well. That should result in a smaller frequency sort of addition once we've achieved that. So I'm going to put my I and my S. Again, I'm writing the I on the left purely because it was on the left here, and the S on the right purely because, again, it was on the right here. There's no, again, strict rule about that. I'm just wanting to be consistent. So in the same way that I did it with the D and the M, I'm doing it again here. Again, each of these had a frequency of 2, so therefore combined they have a frequency of 4. And again, there's no other frequency of 4, so they're going to go right to the end of the queue. Let's continue. So we now are going to combine A, C, and D and M. So therefore I'm going to bring A up here. That's got a frequency of 2, and therefore when it's combined with there, it's going to have a frequency of 5 altogether. And again, I'm going to move it here. Clicking up a little bit now. Again, we're looking at E and N. Neither E or N are currently again in the tree. I'm going to put them just over here while there's some space. So E and N, they each have a frequency of 3, and therefore combined will be 6. Again, they're going to go towards the end of the queue. Then look again, we've got SP, who's going to join together with IS. I've got IS as a tree, and again, it's going to be onto the left-hand side of it, so I'm going to put it here on the left-hand side. That's a frequency of 3, so therefore combined, they're going to be 7. And again, now they're going to move to the end of the queue. And you can see the tail is moving along the queue. So in other words, once we've completed it, once the tail reaches the end, we'll know we've completed the entire data set. Now again, we've now got ACDM combining with EN. And again, notice the EN is on the right-hand side, hence I actually drew it in the right place before. So therefore I'm just going to add 5 to 6, which will therefore be a cost of 11. And therefore again, we'll go to the back of the queue. And then I'm left with just the 2 of them in the data set, and again just join those 2 together, so therefore 18, like so. What that meant then was that we had a tree that looks like this. And what we do with the Huffman encoding tree is anything to the right hand side we give a 1, and anything to the left hand side we give a 0. So in other words, I can just quickly fill this in. You can see that I'm just putting all the zeros in on the left hand side branches, and then I'll put 1s in on all the right hand side branches, like so. Again, you can more clearly see what I've done. What we need to do then is create a dictionary from this. What I mean by that is we're looking for wherever the letter is, or the character that we're using, and then what path it follows. So to get there, I've gone past an O and an O. So in other words, just give that the value O and O, whereas N is over here. So to get there, I've gone past 3 1s. So 1, 1, 1. I'm going to finish that off. So therefore, E is going to be 1, 1, O. A is 1, O, O. S will be O, 1, 1. I will be O, 1, O. C is down here, so 1, O, 1, O. M is right at the bottom down here, so we're going to have to go 1, O, 1, 1, 1. And D is 1, O, 1, 1, O. 1, O, 1, 1, O. Okay, so just giving you a neater version of that. Now that we've got the dictionary, we can now actually create sentences from this and use the data values to do so. So in other words, I've got a sentence here, Dennis is a menace, and therefore what I want to do is look at the value of D, and you can see the value of D is 10110. So in other words, I'm going to write 10, 110. Then I'll look at E, which is here, so 110. N is here, so 111. Again, 111 for the other N. Then we have 010 for the I. S is 011. The space is 00. I again, 010. S again, 011. Space again, 00. A is 100. Space again is 00. M is a long one, so 10111. E 110. N 111. A 100. C 1010. And then finally E is 110. Again, I'm just going to give you the neater version of that. The thing to notice with this is that we should now hopefully have created compression. So the idea of it is that if we can add up all of those bits, with those 1, 2, 3, 4, 5, 6, 7, 8, etc., moving in that direction, we will have 56 altogether. And therefore, it's taken up 56 bits of data. If we'd use an alternative method, such as ASCII, ASCII will generally use 7 bits per character. Because we have 18 characters in the sentence of Dennis is a menace, including the spaces, we therefore would come at a cost of 126. And obviously 56 is far fewer than 126, and therefore we've made a saving. Like I said before, though, the downside of Huffman is we should really include the value of the dictionary as well, and therefore the actual benefit is going to be less as a result of that. And there will be circumstances whereby, having created the dictionary as well, we haven't necessarily compressed it at all, and therefore we have to be careful with this and use it appropriately. The other side to this that we can do is we can have a binary number like so, and we can actually then decode it and understand what it's saying. So the way we can do this, I can either use the table at the top or I can use the tree below. And what we're doing is once we find the code for a letter, we stop. So in other words, I start with 1, and therefore I'm going to come down this side of the tree. Next one is O, so now I'm going to go left. Then I've got another 1, so I'm now going to go right. I've got another 1, so I'm going to go right again. And then I've got an O, so I'm now going to go to left. I've got to a letter of D, and therefore I know that these 5 letters here represent D. I then look again, so I've got 1, 1, and then O. So I've now found E, and therefore I know that these 3 now represent E. And I just keep going. So 1, 1, 1 is N, and therefore N. I've got another 1, 1, 1, and therefore, again, another n. I've now got 0, 1, 0, which is an I. We then have 0, 1, 1, which is S. We then have 0, 0, which is a space. Then we have 0, 1, 0, which is I again. Then we've got 0, 1, 1, which is S. We've now got another space because we've got two O's. And then we've got 1, 0, 1, 1, 1, which takes us back to M. Now we've got 1, 1, 0, which is E. Then we've got 1, 0, what have we got? Sorry, 1, 0, 0, which is A. And then finally, to finish off, we've got 1, 1, 1, which is N, and Dennis is mean, which makes sense, doesn't it? Okay, thank you very much for watching. I really hope you found that useful. Please do let me know in the comments below if you've got any questions at all. Really nice to hear from people and kind of answer questions that they've got. Really do want people to understand this as best as I possibly can. Okay, well, hopefully see you again. Thanks a lot. Bye.